Hello everyone and welcome to today's webinar on tips and techniques for working with large and high resolution data sets. So today we are really going to be focusing on, yes, as I said, tips and techniques for working with that type of data. But I think it makes sense to start with just a reminder for why we, in particular at Softtree, love to work with this type of data. So LiDAR and other high resolution data sets have a lot of benefits in road design. They have a lower acquisition cost for large areas and projects. They're fairly accurate. The survey data covers a large area, giving you the ability to compare and cost multiple route options. And with that comes reduced field time as you've spent more time evaluating different routes in the office. So when it comes time to go out to the field, you're now asking the question, instead of asking where should I put my road, we're saying why shouldn't I put my road here? So by incorporating high resolution data or similar LiDAR into your planning process, you can greatly reduce that time you're spending and improve the quality of your plan. So today's plan for today's topics, it's going to start with me. I'm Erin, the Business Development Manager at Softtree. I'm going to go through some introductory concepts just to cover a little bit of what we're going to talk about from sort of a more of a high level. And then I'm going to pass it over to my colleague David, who is going to talk through some of these concepts in much more detail and show you how to actually implement them in the software. Now at Softtree, we like to think that RoadEng and our Terrain Tools product are pretty amazing at handling long roads, LiDAR, and large data sets, but there's always limitations and there are ways to improve your performance. So the tips and techniques that we're going to discuss today really should help you to get more out of your terrain model when you're working with these larger data sets. So I was just going to introduce some of our topics for today. So I'm going to go through some introductory concepts. Then David here is going to talk about strategic thinning, the usual area of interest definitions with polygons and corridors, and talk about a few different thinning and AOI examples with grid and raster DEM data, as well as LiDAR data, bringing in that area of interest at read time and thinning after, and why you might actually want to do that. Then we're also going to talk about feature grouping, when it's done automatically to save memory and how you might want to do it if you're working with a different type of data. Then we're going to talk about contours and how they can be slow to draw and some of the ways that you can speed that process up. And then lastly, talk a little bit about updating a reference topo. Hopefully you can still all hear me as we go to the next piece of content. But just to let you know, RoadEng and Terrain Tools, I should say Terrain Tools is a part of RoadEng, and today we're just focusing on the terrain modules. We're not looking at a full road workflow. We're just looking at the terrain module itself, which is also available as just Terrain Tools. So let's talk about those concepts. The first concept I wanted to mention is really that there is a data size limit. Our software is not a GIS software. We are constantly creating and modifying surfaces. So there is a ceiling for the amount of points your model can handle. In this example, which the words say 25, the tiles have 30. It did have, say, 25 to 30 tiles. We definitely do not recommend importing those all at once at full resolution. Instead, there are some different things that you can do in order to be able to still work with that large amount of data, but to not crash your computer or really bog it down when you're doing that import. So instead of importing 25 tiles or 30 tiles all at once, you could import smaller groups of tiles at full resolution. You could import all the tiles, but with a reduced resolution, and David's going to show you how to do that today. Or you could import all those tiles and leverage some strategic thinning like an area of interest to help reduce the point count, but still keeping it at full point count in the area that you're interested in. So we're going to take a look at those examples. It is definitely worthy of mentioning that we do have a recommended point maximum in our software. That's around 10 million modeled points when you're using the 64-bit version. If you have more RAM though, that generally ends up equaling more points. So if you're working with a typical business grade laptop, 10 million points is again the ceiling lower points are going to keep your model moving faster, and if you've got more RAM, you can probably increase that. So the next concept I wanted to introduce is this idea of gridded data versus raw data. And in the very rough example image we've got here on the screen, green dots are the raw data. The grid is interpolated from that. And whenever possible, if you can work with the raw data, it's better. You have no unnecessary rounding that's happening, and you're not adding just extra points without resolution improvement, which is what gridding data does. It just adds unnecessary points, essentially. But if you are working with a product that has been gridded and you don't have that raw option, it's totally fine too. But if you're presented with the two choices, raw data is always best. So the next concept, which David will speak to in a fair bit more detail, is this idea of feature grouping. So grouping multiple points per feature, again, is one of those things that we can do that's going to help to save memory on our computers. And LAS, LAZ, and our raster DEM formats, when imported into RoadEng, automatically do this. But if you're working with something, say like a LiDAR file, but it's given as like a text file or a CSV file, when you're setting up that import, it is definitely highly recommended to avoid making those one-point features. So again, leveraging feature grouping, and we'll talk to that in today's webinar. The final one, which is probably of all the concepts I'm introducing here, one of the most significant, we see this all the time, is support tickets. And this is the idea of contours. And contours themselves, when you generate them, can be really large data sets. Dense contours contain tons and tons and tons of points. They take time to draw, they take your memory, and they significantly increase your file size. And it's really worth mentioning that contours do not represent your surface. They're just there for visualization. That surface is your underlying TIN model. So when we add contours on top of it, we're not modifying our surface, we're just giving us something for visualization. So there are some suggestions to work with and to improve our contours and how our computers handling them, including thinning to reduce the point count. And this is something that actually in version 10 can be done when the contours are created. We also recommend, if you can, putting those elevation labels at the end for final output. They're, not necessarily needed when you're doing your design. And then you can also save contours to an external file for flexible background display. So a few different suggestions to help, again, reducing our point count and not bloating the software. So with that, that is my brief introduction. I'm going to pass it over to my colleague here, David, and he's going to take us in now to the software and talk a little bit more about those key concepts as they relate to high-resolution data sets. David?
Good. Okay, so let's take a look at first of all, file types. So we're looking at a data file here, and you really can't tell by looking what the data source was. And I haven't saved it yet, so I'm not really sure. I got two files just like this, and if I actually show the data, there it is. This is a gridded file, so the data is in a perfect grid. And let me just select one feature group by clicking over here in the plan window. I'll pick that one. And there we go. So you can see, first of all, here's the feature grouping we were talking about. We'll revisit this later, but this was a DEM file, and it's a grid, but each grid line looks like is its own feature, and this grid has in it 995 points. So so those points are grouped into a feature, and there's a bunch of them to represent the whole surface. And the surface looks pretty good. I got no complaints with this. It's smooth. There seem to be reasonable shapes that you can pick out of the surface, so it's high enough resolution to see roads and similar. And but it is a gridded surface. Now I'm going to show you the same thing coming from a LiDAR file, and that would be this one here. Now I'm going to zoom in on that same corner down here and show you all the points. And you can see the points are kind of randomly spaced. You can also see that they're not uniformly spaced. They're actually dense in some areas and maybe a little sparse in others. It's quite common to see road features appear as dense areas in a raw LiDAR file, because LiDAR is it's a scan, a laser scan from an aerial device, aircraft or drone, and the foliage, trees can get in the way. So you'll see roads nice and clear because they are not underneath the canopy. And but that leads to a problem with points being, the scan lines here look like they're kind of going north-south. So it looks a little bit like a grid, but it's not really. Those points all in a row are coming from the LiDAR scan, which was kind of going back and forth from north to south. And if I zoom in and do a little measurement here, we can see that these points are quite close together. Those are only ½ a meter apart. And some of them are even closer. Okay, so we've got a whole bunch of data points. This is very close to the raw data. The fact is that the original raw data had returns from the canopy and other features like power poles and buildings and so on. And those returns have been removed, and this is ground only. But still, it's pretty close to the raw data. It's what came out of the instrument, and it's the best we can do. Sometimes this data is oversampled and you want to thin it, but at least you've got it all. It's all here. On the contrary, if I look at that gridded data, I don't know really by looking at the data how accurate, or you know, it's just a grid that's been interpolated. Now, the interesting thing is that the gridded data originally came from raw LiDAR in general, and that LiDAR was made into a tin surface. And I've got an example on the screen on my other monitor. Let me just bring it over here. And you can see here is a situation where we've got a it looks like a perfectly good surface in most places. I mean, we can see the road here, it's very clear. But up in the middle, it looks like there's some large triangles in the 3D surface. Those are not data points that are in the model now. The model is a grid. In fact, I've got a grid line sampled here. There's multiple points going across those flat planar triangles. So here's a situation where in this area, the data was grossly oversampled. I've got a whole bunch of data points in here, thousands and thousands of them, that are essentially representing a plane, which could have been held in 3 or 4 points in a triangular model. Now, that doesn't usually happen. Usually people who build these things are pretty careful, and they try to pick the grid resolution that makes sense. But always, you're going to end up with more, well, not always, but often, you're going to end up with more points in a gridded solution than you will in the original raw LiDAR. So it's a bit of a waste of space. In this case, I've got just under 1 million points because my tile is a kilometer square at 1 meter spacing. And in the LiDAR model, this one, I've got, oops, I don't have a surface in here yet, but you can see I've got about 600,000 points. So I've got a few fewer. So that's the difference between grid and raw LiDAR. And we can treat them both very much the same after we've got the files. But if you have a choice, like Aaron suggested, choose the raw LiDAR if you've got it. Now, sometimes data comes in an ASCII format, and I've got an ASCII file available in a folder here. Let me just find it. So as I mentioned, we can read DEM files. DEM files are the raster grid, and they come in lots of different extensions. The ones I have are TIFF, but they often have a DEM extension. And we can read LAS files. They also can be compressed to LAZ files. And then the other common, but not very common, is the ASCII format. So here's ASCII LiDAR format. Here's a couple of tiles. I'm just going to open one of them here. And the options for ASCII import are flexible. It's important when you do your ASCII import to have a feature grouping. Don't tell me I've forgotten where it is. I think it's in here. Yes, here it is. Feature detection method, but feature size, limit size of features, maximum 1024. And in the code section here, I've got it set up to basically bring all the points into one polyline feature, but I'm not connecting those points. The connected option is off, not connected. So yes, it's a polyline. Yes, there's a bunch of points. They're randomly connected in general. So it would look crazy if I tried to draw a line between each point. That's why they're not shown. The connecting line is not shown here. But they're all going to go into one big feature, except I put in this limitation here. So in fact, what's going to happen, it must have been a programmer put that number in, 1024 being a power of 2. What's going to happen is it'll read 1024 points and say, oh, my feature's full, and it'll start a new feature. And so we end up with a nice model which has not too many features in it and not too many points per feature. And there's the data. And again, this is a classic LiDAR file in the sense that it's a raw LiDAR file, and we can see that there are dense areas. I'm not sure whether that's probably a river, so there's no foliage there. And there may be other features in there as well. Okay, so now let's get on to data preview. What if we have a really large amount of data and we're not really sure where it is or what we're going to do with it? We just want to take a look at it. So I've got a good example of that here. I've got on my computer one other really good thing about the DEM format. Let's just look at all possible formats for a second here. Where is that? All supported, right. LAZ files are pretty big. TIFF file with even more points. Remember, the TIFF files are about 1 million points, and the LAZ files here were around 600,000. Way, way smaller file. So from the point of view of saving space on your hard drive, I have to admit that the gridded format is a really nice format. It's very small, so easy to email or store large numbers of them. Both of these formats can be read in. Did I say file open? I did. With file open, you can choose one, and that's all you can do. But with file insert, you can actually choose multiple files. It doesn't matter whether you've already got some stuff in here or not. You can choose as many files as you want. There is a limitation, but I can't remember what it is. It's 500 or something silly. Anyway, there's all my LAZ files, and I can just click on open here and bring them all in. Now, the problem with that is there's a lot of points, and I think the TIFF read in quicker, so I'm going to use those instead. So there's all my TIFF files. I'm going to read them all in, and Now, 7 times a million points is not a problem. RoadEng can easily handle that. But if there were 100 tiles, or if they had 5 million in each tile, I'd have a problem. So if I want to reduce that, I can just thin it. And this is a great way to work with DEM files. Thin the data at read time. It turns out that the skip 3, read 1 for a DEM is actually skipping 3 rows, reading 1 row, and then skipping 3 points, reading 1 point. So it's actually reducing the number of points by quite a large amount, not just a factor of 4. I've set it to reduce the number of points that are being read right from the hard drive, so I never fill my screen with too many points. So if we zoom in on this and take a look, by the way, when you do file insert, it always selects all the points. So often the first thing you want to do is just hit cancel or click somewhere where there's no data, so you don't have this large number of points being drawn. But anyway, here's my tiles. And if I look at that, you can see the grid points there. And I can measure between them, and they should be 4 meters apart, because the original grid was 1 meter, and I skipped 3, read 1. So I've got 4 meter spacing instead of 1 meter spacing. And that reduces my data a lot. And now I can create a model without, there, I just hit the escape key, so it didn't continue drawing it, just drew this hint of where the data is. Or I can click out here, and now there's nothing selected except my tiles, my tile boundaries, or nothing visible, sorry. Which is another good point. When you're working with large data sets, the data points themselves should be displayed off. So here my boundary is set to be displayed, but my data points have that turned off. Okay, well, I've got a nice model I've already made, but let's just quickly make one here so you can see that process. So I go into terrain modeling, generate. When you read a DEM file, just one of them, it creates a model automatically. It's an option. But when you read a bunch of them, you have to do the calculate later. I know my points are 4 meters apart, so I could say, well, I don't want any triangles bigger than 7. That will fit across the diagonal, but it won't join 2 points. It won't join across these gaps here in the corners. Anyway, contour, sure, that seems reasonable, and let's do that. Now, generating contours, as we mentioned, can take up a lot of space, and you can end up with a lot of points just in your contours. So it's worth mentioning that in version 10, thinning and smoothing is built into the terrain calculation dialog for contours. So here I'm automatically thinning my contours, so I get a smaller number of points in each contour. Right, so now I've got a surface. This surface extends across all my tiles. It's low resolution, but maybe good enough to do some preliminary checking and certainly to look at the 3D surface and see what it looks like. And those gaps there are interesting and something I'm looking into now as to why my tiles weren't touching each other. But anyway, so here's my surface, and now I can do anything I want with it, realizing in the back of my mind that this is a bit lower resolution than I can get, but I've saved myself the trouble of bringing in too many points by doing that thinning operation. Well, I might as well jump to the last topic because we're kind of right there. So if I were working in the location module and building a road, and I really didn't know where the road should go, I could use that large thinned model and build the road anywhere inside those tiles. I've got cross sections, I've got grades, I can see what's going on. I've even got a 3D view if I want it. And this is what I would call a preliminary design. Probably don't want to get too much into the details because my surface isn't that accurate, but at least I can see where I want to go. And I can move my road around, find the right spot. Now, we'll come back to this. Let's take a look at strategic thinning. By the way, you can do the same thing when you bring in a LiDAR point. I'm going to, delay the strategic thinning for a second. Let's see what we would do in the same situation with LiDAR data. Now, I can do the exact same operation. Let's start with an empty terrain here. I can say insert, and I can pick all my LIZ files. Now this takes a little while, so I'm not. I'm just going to take the first one and open them. It will give me the option to do a thinning operation, but this thinning operation is uniform across all the data. And we've already seen that LiDAR data can be non-uniform. There can be sparse areas and there can be dense areas. So if it's possible, and in this case it certainly is, I'm going to read in my LiDAR data with no thinning at all, and then do a post-read thinning operation. You can see why I didn't want to do all 7 tiles. LiDAR takes a little longer to read than the grid. And there's all my data points, and I don't want to see them all. Let's just cancel that. Okay, I'm going to zoom in on the corner here and display all the points. And let's zoom out until we can kind of see what's going on. So you can see that there's some dense areas near the road here. Yeah, I guess that kind of explains. It's not as much variation in the density as there was in that ASCII file I read, but you can definitely see that it's more dense here near the road, and yet there are some very sparse areas away from the road, maybe under the canopy. I'm not sure what these lines are. They might actually be skid roads. I'm not really sure. Anyway, so I want to thin this down, but I want to take advantage of a thinning tool that we've got called Simplify, which will leave you with uniform data. So first, let me thin this down to 1 meter. Now, there's 2 ways to do this. Basic grid simplification, what it does is it creates a grid over your model, and it leaves 1 point in each grid cell. So if I make a 1 meter grid, that's in this case 1,000,000 cells, it will leave me with 1 point per cell if there was already a point in that cell. Otherwise, it'll do nothing. So if there's 5 points in a cell, it'll leave 1. If there's 1 point in a cell, it'll leave 1. If there's none, no change. So that this is not very much. This is still high resolution. 1 meter spacing is still high resolution. Let's see what the results are. So it did reduce the data, and you can see it now looks more uniform. The sparse areas are the same density they were before, but the dense areas are reduced a little bit, and I've reduced my point count from 600,000 to 400,000. So it's a little bit of an improvement. And I could do that same operation for higher thinning, I guess, fewer points. lower resolution. There's a couple of options here too. This one is nice. Sometimes, if you set your grid spacing too small, you have too many points in it or too many grid cells. Similarly, if the data is too large, like it spans multiple kilometers, you may not even be able to do a 1 meter grid spacing. So what you can do instead is this other option here, closest point removal, and they're slightly different. So you can have a bigger grid, maybe let's say 30 here, and then you can say, well, any points that lie inside that grid, they must be at least 10 meters apart. So points that are closer than 10 meters, one of them gets removed, and we use that algorithm to go through the data and find places where it's sensible to remove points. And again, if the data is sparse, it won't touch it. If the data is dense, it will make it thinner. Now I'm going to really reduce my data set because my minimum distance between points here is 10 meters. So I'm expecting quite a lot of reduction, and in fact it reduces it down to 10,000 points, which is not very many. And again, very nicely uniform. Now if I did that import again, and I did the same thinning operation from my LiDAR file, there it is, same file, and this time thin it down 1 in 10 points. Now I'm getting a very quick thinning operation. It requires no effort on my part, but the results end up with non-uniform points and therefore not great. So yeah, I've reduced my data set a lot. There's only 66,000 points here. That's a tenth of what I had originally. But the data is still dense in areas and sparse in others. And in those sparse areas, it's way more sparse than it was. So we've got very low resolution here. Okay, so now that's just gross thinning. What about strategic thinning? So I'm going to, I see there's a couple of questions. We're going to get to those at the end, don't worry. And some of them will definitely be answered before I'm finished talking because I'm going to cover those points. Right, strategic thinning. So I have, remember, a location design, and that data now tells me where I really want to know what the ground looks like. I want to know, I want very high resolution data near that corridor. So I can export that corridor, and I'm just going to save it as a terrain. That's the simplest way to export a corridor from our location design. I've already got one in here called alignment TERX. I'm going to just save on top of it, and all I care about is the center line. I'll remove those, and I don't care about cross sections. There. So now I have a terrain feature. Oops, it went to the wrong monitor. Let's just bring it back. I have a terrain feature which has a lot of symbols on it that I want to get rid of. And it looks like my center line. It's georeferenced. It's my area of interest. Now I can also draw polygons. Let me just do that. I'm going to draw a polygon. Call it AOI. And I'm going to draw it. It doesn't need to have elevations. Draw it with the mouse. And let's just close that. Okay, so this is now an area of interest. Two different ways of representing that area of interest. One is a alignment that represents a corridor, and or the center of a corridor, and the other is a polygon. Let me save that. Now I can strategically thin my data. So there's two ways to do this. You can do it at read time, which is a great way to do it if you've got DEM data, because as we saw, the DEM data, whoops, I don't want to open, I want insert. The DEM data is really smart about how it thins when you do it at read time. So there's all my TIFF files. If I sort by type, it should be all, oops, that didn't help. Okay, so I'm going to import those. And do exactly the same thinning, except I'm going to do it on the corridor. Now I could do it on the polygon or the corridor. Oops. So I do need to have the feature in my terrain before I start. And that's the corridor center line. And I can choose the corridor width here, so 100 meters each side. Now that I've got two regions, default, I could either skip it or thin it. And the original, well, skip 0 or high resolution, no thinning on the corridor, but reduce the number of points outside the corridor. And how many files do I have here? You know what? I can just skip to the end here, and yeah, I'm going to cancel this and open the file. It's already been created. It takes a little bit longer to read any file when you're doing thinning, and here's what it looks like. And if I zoom in on an area here so we can see the corridor and then display all points, you can see exactly what it's done. So that's what we call strategic thinning. The data near the corridor center line is full resolution, 1 meter spacing from the grid, and out here is 4 meter spacing. The total number of points is only 1 million, so it's reduced by a factor of 7 from the original data set. And again, I want to emphasize terrain and RoadEng in general would have no problem with 7 million points, but for the sake of argument, we could pretend that would have been 70, and now we've put it down into a range that's quite reasonable. Now, doing that same operation on the LiDAR data would produce a data set that was non-uniform. But it's possible to do strategic thinning after read as well. And I'll just show you the results of that. So here's the file that I created earlier today. There we go. And if we zoom in on that, and again show all the hidden alignment points, and just type in Control A, you can see here that we've got dense points near the center line. That's 100 meters there. Here's my thinned data. So we've got strategic thinning, but this came from the LiDAR. So I'm not going to actually do the thinning operation. Again, it takes a little while when there are areas of interest involved. But I did it again. I read in all the data points. And because there's only, it's not even 7 million, it's probably 5 million, I was able to do it in one go. But if I had 100 tiles, I might have to read 5 or 10 tiles at a time. But you can read way more points then you can actually calculate into a surface. And so you can read the points into the terrain module, use the simplify operation to reduce the number of points, and then calculate your surface afterwards. And the simplify operation, which I showed before, has two modes, basic and closest point removal. Also has this option of creating regions. So again, I can create a corridor or a polygon from existing features. So there's a polygon, and here's, oops. You can also type in rectangle coordinates. Nobody ever does that. It's way too much work. Corridor, and my corridor is called H-align. And now I can do, again, set the corridor width, and I can do a very similar operation here. This is now an excluded region, and I can do data thinning outside of it. So what I actually did here is I did two steps. The first step was to thin everything down to 1 meter without an excluded region. And then I thinned outside the excluded region down to 10 meter spacing. And that is the result that you can see on the screen now. And because I used the simplify operation after reading the non-uniform LiDAR, I ended up with quite uniform data. And it's sort of the optimal solution. There's no redundant points, no points sitting right on top of each other, and they're nice and close together for accurate cross sections. Okay, so I've created this file, I've saved it. Now I want to go back to my road design, which is still open, and simply swap out the terrain. So currently you can see here the background terrain is called topo all thinned. I can do that, see that here too. My topo surface is called topo all thinned. I can just change that. So I've already saved this file, topo strategic thin. Yeah, it's bigger. That makes sense. It's got more points in it. And I open that up as my new topo and recalculate the alignment and the cost, and watch the cross section here. It becomes a little more detailed, and my volumes are a little more accurate. Same with my profile. Everything's more accurate than it was. More details. That's the idea of low-res recce or proposed road alignment, and then high-res actual road design. Well, I think I've covered everything I wanted to except for contours. So let's get into the contours themselves. I'm going to go back to that same model in the terrain module. Don't forget you can switch modules here too. Gets a little confusing when you've got multiples of each, but I've only got one location, so I can jump over to location from here. Right, so contours. There's not very many in this model right now, and that's fine. The surface exists whether the contours do or not. This surface, which is being used in the road design for calculating cross sections, is defined by triangles. And I can show you those triangles here. It's called a triangular irregular network, or TIN, and there they are. There's all my triangles. That's the surface. The contours are just there for visualization. I can add more or remove them, and it's quite easy to select the contours and save them as a separate file. So let's make a little denser set of contours and do that. So in my generate here, we can calculate the triangles again, but there's no need. and I'll recalculate the contours. So let's make them a little more dense. Let's go down to 5 meters and major at, say, 50. Labeling. These can cost you, and it depends on your scale. So here, if I turned on labeling with things zoomed out at a very large scale, I wouldn't get very many labels. Wouldn't be a big deal. If I had zoomed in and my scale was, say, 1 to 200, I'd get lots of labels when I zoomed out again, and it would be a giant mess. So my recommendation is don't even use elevation labels when you're contouring until you're ready to create something that's ready for output. You know the scale you're going to output at, and then the contour spacing will make sense, and you'll get whatever you're looking for. So I'm going to skip labeling, but I'm going to make the contours fairly dense. And here's the thinning smoothing. This says remove all points that won't change the contour position by more than 1/10 of a meter. And our data points are only a meter apart, so 1/10 of a meter in the contour position is not a big deal. This is still very accurate, but it reduces the number of points in the contours. Smoothing adds points, and then thinning removes them again, so sometimes I just leave that one off. And the software is pretty smart about picking the right defaults, but if you want to look at thinning and smoothing, it's right there. So now when I create my contours, they will automatically be thinned down, so there won't be too many points in the contours themselves. Now that's quite a dense set of contours, and it draws pretty quickly. That's not a problem. If I hadn't thinned it, the draw time might have been a bit slower. Now, I want to make this into a separate file so I can put it in the background. I just go into select features, and don't forget all these things. I love to use the right mouse, but all these things are in the ribbon too. So I think that's in the home ribbon, select, by name. The contours all start with CNTR. They're CNTR and CNTR-M for major. And the easiest way is to go into the advanced section here and just type in CNTR star. Make sure there's nothing else selected. Select CNTR star. There they are. There's 242 of them. And in that selection, there are 54,000 points. Now, if that was 5 million points, it would take a long time to draw, and it wouldn't give me anything except lines on the screen. It doesn't help with the surface, and it may just be a waste of memory. Okay, so I've got them selected, and now I can copy them to the clipboard, Control-C copy, and then just start a new terrain. I didn't really make any, I did make some changes here. I made the contours different. That's all right. I'm not going to bother saving this. I've got those contours on the clipboard, and I can paste them. There they are. So here's a data set that is just contours, and it has in it, like I said, 54,000 points, and now I can save that. So I'll call it contours 5 meter, and it's in the right folder. And now in my location module, for example, there's the low-res contours that are in the background. And now I can add, and this could be in a terrain too, location and terrain both have the same background options. I could take that one and turn it off. And, whoops, that's not the right one. Yeah, that's the one. This is roads. Yeah, okay. And then I'll add my contours model. By the way, if you put an image in here, the image should go first because it's opaque. And then the other ones draw on top of it. Anyway, it doesn't matter where I put my contours. That's a good spot. And I can turn on plan display for that. And watch out. Sometimes the washout factor may be not what you're wanting. 0 is full dark contours, and say 80% would be washed out, very faint, which is nice sometimes because then it doesn't interfere with your foreground line work, like the road edges and so on. Anyway, I'm going to do that. I've got my contours. They're washed out at 80%, and there they are. Now that means I can simply go in here and turn them off anytime I want. And I can display them in any document. The only downside to this, well, that's not really a downside, if the model changed for some reason, I would have to recalculate those contours. But this is my original ground topo. It's not going to change. Right, that's what I wanted to cover, and the important thing here is that there is a limitation to the amount of data you can fit into our software. So don't bring in too many points. Don't display points that you don't need to see. And if you need to thin your data for LiDAR, I strongly recommend that you use the simplify option because it takes non-uniform data and makes it more uniform. For grid, you might as well thin it at read time because it doesn't make any difference. It's going to do a very nice uniform thinning operation anyway. Right, let's take a look at some of these questions.
And while you take a read of those questions, David, I just want to put out, I guess, a little public service announcement. So today was all some tips and techniques for importing and working with this data. And on December the 15th, we do have another webinar, and we're going to be focusing on showing you road design using LiDAR data, the full process, more of a full workflow webinar. So be sure to check that out up on our softtree.com website. And with that, David, are you ready for your first of, I think we're probably going to have time for 2 questions. Ready for your first of 2.
Okay. Well,
Excellent.
The first question is, oh, are you going to read them for me, Erin?
I was going to read them for you, and
okay,
I was actually going to go with
the
third one on the list just because I like the question because I think it's interesting.
Okay.
Can contours be denser for a corridor or a polygon and more sparse outside or absent outside that polygon?
Well, that's a hard question. The answer is yes. The way that you do that is a little tricky, but you can certainly do it. The trick is to build the contour set. I think maybe the way to do it would be to import the data. One way to do it is to save your dense contour set and your sparse contour set to separate files and then import them. And does Terrain allow that? If I do an insert file here and I pick a terrain, no, it doesn't have it. Okay. No, what you would need to do is you would need to use a polygon to actually break and then delete, select outside. So it's a couple of steps to do that process. It's not automatic. I'm not going to show that now for time purposes, but if you want to see detailed steps for that, please send us an email. We can reply. Next question.
Excellent. We're going to make this one the last one just because we're right at the end of our designated time, which is how do I combine a CSV alignment with my LiDAR data? My CSV is higher accuracy and I want to combine it
Okay, so the CSV
with the LiDAR data model.
Right, so the CSV data is high-res survey. I'm guessing maybe total station or something. And the LiDAR data is high resolution but slightly lower accuracy. well, let's put it this way, dense points but lower accuracy. LiDAR points are usually around 1 decimeter accuracy, 3 or 4 or 5 inches, and the total station, of course, is millimeter accuracy. Well, the trick is to cut out a hole in the LiDAR and insert your, it's actually not so different from that contour question in the sense that you need to remove a piece of the LiDAR data and then insert the survey data in the hole and then rebuild your model. Now, this is not all that difficult unless you've got a slight misalignment. If your survey data, your high resolution millimeter accuracy survey data is actually a meter or half a meter or 2 meters different from the LiDAR because they're not properly referenced to each other, then it looks like crap. You get a big cliff between the two surfaces. So making sure that they are tied to each other requires a bit of work, and it's usually done at the survey level. Surveyors are good at doing stuff like that. It is possible to do it in our software, but it's not trivial. If it's simply a question of changing elevation, easily done. If, however, the survey is a meter low at one end and a meter high at the other end, not so easy to make them line up. But it's easy to bring the survey data into a hole in the LiDAR data so that you've got survey in one zone and LiDAR in the other zone. It's not that easy to make sure that the place where they meet is smooth. Well, thanks very much, everybody. If you have further questions, and some of these questions we will follow up by email.
Yeah, thank you all for coming. And we look forward to seeing you again at another webinar in the near future. Bye, everybody.